of f of x, if y is the inverse of f of x, then y f of x equals f of x y equals e to the h. Right? That's the definition of an inverse. Right? It cancels out in a sense the other one. So if y is the inverse of f of x, yf is equal to fy equals the unit. Right? So that's what we're trying to prove. Now we're trying to prove that y is equal to f. So we know that's the inverse of that. Right? It's just obvious because it's just the same inverse. But what we're trying to prove is this inverse here is equal to this. Right? In other words, if we map the inverse in G, we get the corresponding inverse in H. So we're trying to prove that. That's obvious. Right? We know that. Okay. So if y is this, if y is the inverse, then multiplying this on the left by that should give us e. Right? It should give us e. Yeah. The inverse, well, supposed inverse, f gives e. Well, we've done that there. We've proved it. All right. Now let's try the other way. So we'll put this then on the right hand side of f of x. So we'll get f of x equals f of x inverse, and that by this again, that the order's now changed. It's now x inverse. So that's x inverse, and that's still little e. That's the unit from G. Okay, and that's the same. So this will just be e of h. All right. So we've done it. Okay, because now we've got f of y, and we've proved it. Okay, so all right. That's proof of theorem 35. Now, the next part, a bit harder and a bit longer, is in the textbook on page 94. It's example 1131, and this will be an example of how you go about proving that two groups are isomorphic, and it's not trivial, and it will illustrate. It will use actually three main criteria for proving that two groups are isomorphic. Now I've mentioned these two already a couple of times. If you have a mapping here between two groups G and H, and you're told G and H are isomorphic, then you know that F, that mapping, is bijective. It has to be one-to-one. You're in a sense translating the elements of group G into the elements of group H. So it has to be bijective. But that's not enough. You also have to prove that the corresponding elements of each group table map also. So you need this criteria. Now, what about this one? It's sort of new. You haven't seen this before. If you're given two groups, and in a moment, I'll give you two groups, and you're asked to prove that they are isomorphic, you may have to start with a hypothesis of what F is. Right? You may have to guess or reason what is a reasonable F, right? Because if you're going to show two groups are isomorphic, you have to map them, right? You have to find some F, some function, right, that maps one group into the other. Now, your guess, your hypothesis, for f, your proposed f, is it reasonable? Does it, when you use your f to map elements of G into H, is the result, you know, these elements that you're getting, like, do they belong to H? Like, is this function, this proposed mapping f, is it well formed? Does it make sense? And that may not be too clear at the moment. We'll do it a couple of times, especially in the problem-solving portion of this lecture. So you'll get the hang of it after a few times. So in a sense, in reality, in practice, there are three things you need to keep in mind. Your f that you're proposing to perform the mapping between G and H, these two groups that you suspect are isomorphic, and you're trying to prove that. So is your mapping, your f, well formed? So that's, in a sense, your first criterion. You have to show that it is. And in this example I'll do, I will show that. I'll give you an example of what it means in this particular case of well formed, you know, making sense. And then I'll show that it's bijective. Now, this splits into two parts effectively. Remember, bijective, by definition, is a mapping, you know, function that is two things. It's injective and it's surjective. Right? Remember that? We've done that extensively now. You should be well versed in that concept. So in a sense, in a matter of speaking, you can almost say it's like four parts, right? Because one, and this splits into two parts, and this one. And you also have to prove that. All right, with that as preliminary, let's pose the problem. And here it is. So it's this example number. And you're asked to show that Z of 6 is isomorphic to Z of 2 direct product Z of 3. Okay, now remember, be warned, Barnard in this text, this text uses this symbol in two ways, and it just swaps around. So you have to be careful which meaning, which use he's using. Now, in this particular example, these z's here are not just a set of simple integers. They are the other use. They are sets of residue classes. Right? A residue class, remember, is an infinite set of integers. Like, for example, this is the residue class of 0 mod 2. And what does that mean? It's an infinite set, right? Countably infinite. It's the set of all integers that are, what's the word? Damn. Congruent? Congruent. Right? It's the set of all integers that are congruent to 0. Right? Mod 2. And if you're fuzzy, if you don't remember what if two integers are congruent, if you forget what that means, go back a couple of lectures. Anyway, so in practice, that would be like 0, plus or minus 2, plus or minus 4, plus or minus 6, plus or minus 8, and so on. So in other words, all the even integers. Right? And this one this element here of this set, it's a residue class, and it too is an infinite set, countable, and it's the set of all integers that are congruent to 1, mod 2. So in other words, it would be 1 plus minus 2, 1 plus minus 4, 1 plus minus 6, and so on. Okay, so the odd integers, so the even integers and the odd integers. Okay, now, well, so that's Z2. So we've explained what Z2 is. Now Z3 would just be one more of these. So you'd have, but now it's 3. The modulus is now 3. Okay, so that's Z3. And Z6 would be 5. Okay, so that's Z6. And you take these two groups. Now they're groups. We proved that quite a few lectures back, that these sets, that a set of residue classes is a group. Alright, so you're asked to prove that this group here with 6 residue classes